Yeah, I finally got in Shanika. Good afternoon. Share this in there. Go put my laptop away. That in here. And when I come back in is when I'm gonna lock the daily quiz. So make sure you got your answers in. And I was at 30 seconds, but it's similar. Yeah, you can't log it. Yeah, I had to go grab my laptop. Yeah. Down the bottom. You can do. Oh, okay. Yeah, that's in there. 1, 2, 3, or 4. Oh, no, it's switch over. 1 is here, 2, 2, whatever. Oh, okay, it's that other thing. Okay. I think that you probably had against that. Yeah. All right. That's cool. Thank you, IT. Don't worry, I won't. So that's maybe I found something interesting that we can do on the screen that I had no clue about. I think some of the students kind of intern part-time with IT. All right, but blocking answers in 3, 2, 1. Answers now. All right, you only get 4. I think you got 4. I'm going to accept one answer, even though it's technically incorrect. I'm going to pick on. So I get to pick on Shanika. So it's approximately 2 to the 88 power. It's not equal to 2 to the 88 power. 26 factorial, not the same. But you did also recognize that it's coming from S26. And I think everyone else did. 26 factorial. 26 factorial different permutations. But the relation was it's roughly 2 to the 88 power. Different ciphers you can choose to encode the message.
Okay, yeah, I see what you're saying. I didn't find that. I couldn't do approximate, and I didn't write out the whole thing, so I just put equal. But yeah,
Yeah, that one I would just prefer. That's what most people did was 26.
26 factorial.
Because that's the exact number, right? That is the exact number. Cool. Any questions before I begin today? Going back to isomorphisms. Got it. Here's the recordings being recorded, or the meetings being recorded. I'm just tripping over my words right now. So what does isomorphism mean? Is Greek for what?
Same or equal?
Yeah, same or equal what? Form. Yeah, there we go. All of y'all got it. Bam. Street. Scroll back down. So, when isomorphism is just saying it's a bijective homomorphism, and what did I say homomorphisms are doing? They preserve what?
Group operations.
Yeah, they preserve group operations. Technically could have cheated. Look at the board, it's right there on the stars. But yeah, it preserves group operations. So real quick, let's do some quick recollection. What does it mean to be a bijective function? Yeah. 1 to 1 and on 2, but if you take a class with me, I use 2 different terms. Injective and surjective. Those are 2 other terms that are commonly used to talk about the same thing. Usually you hear 1 to 1 and on 2 get these are still concepts you introduce even back in algebra courses. And it's a little bit easier to correlate concept of an injective function or one-to-one function with the name one-to-one versus injective. Similar for onto and surject. But what does it mean to be a one-to-one function? So yes, unique output. So how we define it is, what's the best way to do it? Yeah. For all X and Y, and whatever your domain is, this is just even shorthand for mathematics. If your function outputs are the same, then your inputs must be the same. So that's what gives us each input has a unique output. What about onto?
I would struggle with that one. I think every element of X can be mapped onto an element of Y without loss.
So that's one way you can look at it. I would encourage you to change your perspective. Don't think about it coming from the domain, think about thinking it from the range or codomain. So how a onto function is defined, so for all elements in your codomain, so it's the set that you're mapping into. There exists something in your domain such that that output gets mapped. So what did we say in discrete? You know, it's an onto function if my codomain is equal to what other set? What was that, Melissa?
No, I didn't hear.
Oh, very good. So how we define just by sets, we know a function is onto, and this is what we talked about discrete a little bit. If your codomain is equal to what? Range. So codomain was all the set of allowable outputs. Your range is the set of all achieved outputs. If you achieve all allowable outputs, then you're an onto function.
It's too little the same.
Not a lot of people do. That's why I like to still make sure it's clear that that is differentiated. Okay, so that's what it means. So when we're defining when we're talking about isomorphism, what we need is I need a bijective function, so a function that maps from one group to another group. It has to be one-to-one and onto, or injective and surjective, and it needs to preserve group operations or satisfy this homomorphism, whichever one you want. And again, where it's talking about the homomorphism part, I like to draw a photo just to make sure it's clear. Right, so you're going from one group. Oh no, squiggly. I think I did overline last time, so I'll just stick with overline. So from one group to another, right? And it has the property that phi of A times B is the same thing as phi of A times phi of B. So I can take my first group. There's so if I take a group G and I'm using this homomorphism, right? I'm going to just select two elements, A and B. And then I know I can combine those two elements together to get a new element represented by times two. So I can throw each of these three elements through this homomorphism, and it's going to create three new elements inside of that group G bar. Second. Let's just say every one of these lines is my function B. So B gets mapped to whatever B of B is. A would get mapped to whatever B of A is. And similar story for B of AB, right? Each of these three elements will be mapped to. What we're saying is now, if I'm in this new group with a different operation, I can combine both of those two B of A's and B of B's together, and it should be equal to what element? Be equal to B of A, B of B. So it doesn't matter whether or not I combine the two elements in this first group G and then map them over, or if I map them over individually, then in this other group combine them together. It should always become the same element. It should always have that same element. That's what it means to be a homomorphism. And then, biggest note, I don't think I wrote it the other day. So if I do have a mapping from a group G to another group G bar, then it's an isomorphism. Then we would say G is isomorphic to the second group G bar. And we would write the following. And quick visual interpretation, G is equal to, with a squiggly on it, G bar. But since we're not talking about group, or since these two groups are technically sets, sets are only equal if all elements are equal, but we've just said groups can be different, right? They all have different representations of their elements. So the sets will never be equal, but the structure that those elements create may be equal. The form that they create may be equal. And that's what we're referring to here. So, what questions we got so far? So then, how do we show two groups are isomorphic? Well, there's no opposite way. What do we require? So, if there's an isomorphism, then we say the two groups are isomorphic to each other. Meaning they have the same form. But to be able to claim that, what do I need? What is the hypothesis in that statement that I just need to start? Yeah. So if there's an isomorphism, didn't say it has to be a specific isomorphism, doesn't say it has to be only one or multiple isomorphisms. As long as there's an isomorphism between these two groups, I can call them isomorphic. Then if my goal is to say, how can I show that two groups are isomorphic to each other? What is the one thing I need to create or construct? I mean, it's technically a proof. They have to create what and prove it is this thing. You know, the chart, that's only one part of it. What's the term? Right, put thinking caps on real quick. If this mapping B is a what? Isomorphic, then I call the two groups isomorphic. So if I want to prove two groups are isomorphic, then I need to construct an isomorphism. That's doesn't, like I said, there may be many isomorphisms, but I just need to create them. So I've got really just kind of what I consider 4 steps. First step is usually the hardest, because you have to be creative. What you need to do is define some mapping from one of those groups into the second one. And this is going to be your candidate for an isomorphism. But for it to be an isomorphism, we know there's 3 things it has to satisfy. If technically some of them, 2 of them up in with one term, which is bijective, right? But let's break it down a little bit more, because then I would have to still show that the mapping that I created is a bijective function. So what are the 3 things I need to show? Injective or one-to-one, onto or surjective, and then also that it's a homomorphism, that it preserves group operation. So step 2, 3, and 4, it doesn't matter what order you group these in, as long as all of them are shown to hold true. First thing you do is prove that that mapping that you created is one-to-one. And that's why, Chris, I was saying, yeah, technically there is proof here, right? You weren't wrong, this just wasn't the answer I was. So then what would you guess I would list step 3 to be? Surjective. Yes, all right, this whole thing together here. Injective, so then, okay, well, if it's one-to-one onto or injective and surjective, that checks off the bijective part. And step 4 is to prove that this mapping the homomorphism, that it preserves the group operations, even when I travel from one group next. Remember, this means that phi of A, B has got to be equal to phi of A times phi of B for all A and B and whatever my domain is. Okay. So let's do an example. We're going to let just G, our first group, be the real numbers with addition. And kind of that G bar, my second group, to be the positive reals with multiplication. We're going to show that these 2 groups are isomorphic to each other. So first things first, I gotta define a map. And until we start getting really comfortable with what type of mappings might work and what not, this might also or always be just like a trial and error. Right? There might not be an easy one to spot without a lot of experience. So don't be afraid to have to try to come up with a couple, a few of them might not work, then you can slowly start to reason your way to something that may. So if I'm wanting to show that these two groups are isomorphic, I need to define an isomorphism between them, which means I need to first start with a map. So I gotta understand, okay, what set am I mapping from and what set am I mapping to? In this case, my domain, the set of elements that I'm mapping from, is going to be the real numbers. That's in the first group. What's the second group? Positive. So everything above 0 does not include 0 because 0 is not positive. All right. So I guess maybe we're going to say, I'm going to put define before that. And I have to go, okay, what is a way that I can turn real numbers into positive real numbers? There's tons of ways I can do that. But then I got to start thinking in the back of my head, okay, of those ways, what's probably going to be one-to-one, and on to really focus on a bijective function first, and then see if it's going to preserve my group operation. What is my group operation for what we're referring to as a group G? Addition. What's the group operation we're referring to in the second group? Multiplication. All right. Well, the obvious choice, though not the only choice, just raising these two powers or treating these powers as 2. If I raise a positive number to any positive power, or really a negative power, it's always still a positive number. In fact, your graph of 2x, 3x number is always above the proportional axis. And it never reaches 0, even if you were able to go negative. So we know this is going to be well defined. And now what do I need to prove to show that this is an isomorphism? Yeah, to prove it, I need to prove it's 1-to-1. I also need to prove what else? Onto, and then lastly, we'll work this up. So let's just go with showing that it's 1-to-1. So I'm going to take 2 elements from my domain. And assume that their outputs are the same. And my goal will then be to show what? X equals Y. Those inputs must have been the same value. Well, just by how we define the mapping, phi of x and phi of y, I just take the x and y and put it in a power of 2. This just becomes 2 to the x and 2 to the y. And then what can I do to both sides of this equation to essentially end up getting that x is equal to y?
Wow.
Log what base? Log base 2. That will leave me with just x is equal to y. Therefore, this is what that function. 1-to-1, or if you want to say injective. Those are interchangeable. Step 3. Is to show what? All right. So then I need to choose an element for my codomain, which is the set for what my second group is defined on, in this case, real numbers. And I want to say that, okay, this is your target output. I can always find an input that'll map to it. So if I want the outcome to be y, then what can I choose my input to be so that when I plug it into my function, I'm going to get the value y. Well, if you don't know, you can always use some scratch work. I need 2 to some input to be equal to y, so how do I solve for x? I'll do log base 2 of both sides, leaving me with that input, x, would be log base 2 of whatever your wanted output is, y. Will that be a real number? So then all I need to do is say, okay, well, whatever the desired output is, I know I can find an input x, which would be log base 2 of that desired output, which is in my reals, such that b of x, which would be 2 to the x, but how we defined that term x, this means it would be 2 the log base 2 of y. And if I have 2 raised to the log base 2 of y, what happens to that exponent of log base 2? Or what's the outcome from all of it?
What?
Yeah. They cancel each other out because one of your properties is lots. I get that the desired output is y. So any output that you might want to choose, can I find an input that will map to it? Yeah. So therefore, this function's on 2. Or if you want to use surjective, you can use surjective. And now what's the last thing we do? So it's a homomorphism. So I'm going to choose 2 things for my domain. And our goal is to show that if I multiply or if I operate those 2 elements in my first group, then send them through by my mapping, that this is going to be the same thing as if I send them through the mapping and then operated them together. I'm trying to be careful here because I know one of the operations is actual multiplication or just general arbitrary multiplication that we like to use for any group. But really all I need to do is start at one side of this and then the other through a string of equalities. So let's look at my group operation inside the first group G. The first group G was the real numbers with what operation? Addition. So am I applying the first group's operation? Yeah, right? So I'm operating inside the first group, and then mapping it through this function. So what is the output gonna? Don't overthink it. Not 8 times b. How do we define our isomorphism or the candidate to be an isomorphism?
1 to 1.
So we showed it's 1 to 1 and on 2, but how would we define it?
But it's based on X.
Yeah. Yeah, whatever your input is, I put it in the power of a 2. So what's my input here? A plus b. So phi of a plus b is going to result in what? 2 to the a plus b. Now I got to remember I'm working inside of my second group, which is positive real operative person. District. You have to compartmentalize. Remember, this second group that we're now in is the positive reals. What is the positive reals operation we chose for this group? Yeah, multiplication, right? Multiplication of positive real numbers. So I want to see, okay, can I rewrite this as phi of a times phi of b, or 2 to the a power times 2 to the b power? Can I do that? Yeah. Normally we go back to our algebra and say, okay, the bases are the same, I'm multiplying them together, I add the exponent. But I can also break that apart. If I'm adding the exponents together, I can separate this. That's 2 to the a times 2 to the b. And 2 to the a is just the outcome from taking the element a and mapping it through by phi. And similar for 2 to the b. That is the same thing as if I just wrote b. So what have I now shown is true about this mapping? Homomorphism. Now I can compile all of my information together. We have a bijective homomorphism. So what can we now call this mapping P? And an isomorphism. The P going from the reals with addition into the positive reals with multiplication. With an isomorphism. And we can say the reals with addition have the same structure or same form as the positive reals with standard multiplication. What questions y'all got?
Like, any other function that A has to be to that?
Now, technically, you can read the x, 5 to the x, 6 to the x, 7 to the x, 8 to the x, square root of 2 to the x. Those would all be candidates for isomorphisms.
So could we have done something like mapping the first one of each of them to each other? Like, I know that the one with the plus sign would be 0, and then the one for the multiplication would be 1. So could I map 0 to 1, then 1 to 2 to 3, so on and so forth?
So you can't, but it's not because that isn't a bad idea. The issue is the real numbers are uncountable. So you wouldn't, their density is 0, so you wouldn't be able to explicitly define every input and every output. Like you can actually do like integers, natural numbers, or even rational numbers. Technically, you could do it all. It's not a bad thought, but usually with infinite sets, it's best to define a rule like we're used to, like what we did here.
We could just make one up.
Mhm.
So we could have done like 4 together.
Yep.
Or,
To show two groups are isomorphic doesn't mean you have to pick a particular isomorphism. You just have to show that there is an isomorphism. So we're gonna choose a cyclic group generated by an element A, and we're going to assume that the order is infinite. And just a nice little call. We're talking about the group generated by an element A. We're just talking about, okay, what is being created every time I operate A with itself. And saying that it is infinite, we got a result. If that is infinite order, that means there's never a point where I had the ability to raise A to some power and get the identity. Which means it never created this closed loop that we saw with cyclic groups of finite. So that means if I ever say A to the I is equal to A to the J, so I take A and raise it to two potentially different numbers. However, those can only be equal only when those exponents are the same. So what we're going to do over the last 10 minutes, show that this cyclic group generated by A is really just a different form for your integers and addition. That is stated differently, that it's isomorphic to the integers and addition. So I need to come up with an isomorphism between this cyclic group generated by A and the integers. So I need to define something. Anyone have an idea of what we might be able to do? What's the bullet again? We need to define a function that takes elements from the cyclic group generated by A and turns them into integers. And then whatever that mapping is, I want to then show that it's one-to-one and onto an homomorphism. Well, what do all my elements in this cyclic group generated by A look like? Cyclic group, yeah, A raised to some integer for any integer. So I could just be a little cheeky and say, all right, well, since anything in that cyclic group is A raised to some integer K, I can just say the mapping takes whatever that exponent is. So I'm taking elements from that cyclic group and turning them in to integers. So now what's my goal? What are the three things I need to prove once I've defined a candidate for an isomorphism?
Wait, sorry,
Go ahead.
just to make sure, we just created that formula there, or like, is that the only one?
No, might not be the only one. You
Also,
probably
the
create,
similar thing has to do to that.
Yeah.
Okay.
you don't have to create the isomorphism. It's probably never the isomorphism, you just need an isomorphism. Some of them might be difficult to create. But all you need is one. So let's quickly do the next two steps. Let's show one-to-one first. So I need to take two elements from my input. So give me two letters to use.
Yeah.
C and P. So I'm gonna have A to the C power and A to the P power. We're gonna assume that P of A to the C is equal to P of A to the P. Well, if I apply the definition of these mappings that we just created, what is A to the C power going to get back? C. What is A to the P power going to get back? P. Oops. And I know, because of the cyclic group that we're working in as infinite order, we've already studied those. If these exponents are the same, C and P, those two values, that means those inputs, A to the C and A to the P power, have to be the same exact value. Therefore, we've shown you give it two input, or you give it two inputs, you assume the outputs are the same, then that directly implied the input that is the same. What can we call it? Mhm. Next up, gotta show it's onto. So give me another letter. It can be just a repeat, just not little a. J. So if I choose something from my codomain, which is the set of integers, what I'm mapping into, can I figure out an element in my domain, that cyclic group generated by A, that will map to J? Yeah. And I know that there is then an A to the J power inside of that cyclic group, because in that side of the cyclic group is always A raised to some integer, and we are trying to look for an integer. And A to the J power will map to J through this mapping that we've created. And now this B is what? We've shown it's what? Mhm. And the fun one, in my opinion, is to show that it's a homomorphism. All right, Chris has been dominating the letter choice. Look at Melissa or Xander. Give me 2 letters of the middle like.
Okay. Well, you just do it.
It doesn't matter. P and K is fine. Just trying to drive home the point. A lot of these variable choices are just kind of arbitrary. Doesn't really matter. So if I choose anything in there, my goal, I want to show v of a to the p times a to the k is equal to v of a to the p times p of a to the k. I'll just bring it down to 1. But also it can be a little bit more particular. This is what it means in general, but I'm just saying it's a group with multiplication, multiplication is just representative of an operation. But what is the group that I'm mapping into? In this example. Integers with what?
Positive one,
Not positive,
or addition?
with addition. So integers with addition. So really, if I want to be more particular, since I have my example for this particular group, it's not p of a to the p times, where it's that general operation. What's the operation? Plus. Because that addition is the operation of the second group. Why? It's an operation preserving that. This is hopefully going to unlock a little bit of how the proof's going to work here in the last minute that we got. So we start at one end, and work our way to the other. V of a to the p times a to the k. Well, how can I rewrite that element that's inside of that mapping before I apply it? Because I only know what to do with a raised to single power. I've got 2 things. Yeah, so bases are the same, multiply the exponents together. I'm just doing p plus k operations of a. And if I have p plus k operations of a, then b of a to the p plus k is going to be 1. P plus k. I'm just remembering that addition is the operation in this group that I just mapped into. But wait, p is just the outcome from 1.
B of a to the p.
Yeah. And k is just the outcome of b of a to the k power. We have now have provide a nice little strong a string, not strong, but a string of equalities that show whether or not I operate inside my first group and then map it through. It's the same thing as if I map it through individually and then operate together in my second. So we get that P is a homomorphism. And since we have a bijective homomorphism, we can actually call it an isomorphism. We get that our cyclic group generated by a single element that has infinite order is really just your set of integers in disguise. is why it's so interesting. Because everything is related. Everything in mathematics is just a new kind of perspective on existing objects. In fact, if you get into some like the really high level research stuff like this, with biggest results are the following are equivalent groups. You take like 3 random groups that are constructed and show that they're all the same. But already over, so definitely gonna stop there. If you have questions for me, like always, feel free to stick around maths. Otherwise, get on out of here, and I will see you on Wednesday. Have a good day, Shanika.
You too.
You finish your proof, rather
Hmm?
You finish your proof, rather
What do you mean? Check your eyes. Good. And you